In this video, I'll talk about two of the most common fragmentations that would take place in aldehyde and ketone functional groups whenever we run in a mass spectrum. And two of the most common ones would be the alpha cleavage and the McLafferty rearrangements. Now I'll talk about how you see the alpha cleavage, and I'll talk about when you can possibly see the McLafferty. You're not going to be able to see the McLafferty all the time, but we'll talk about that in a minute. So suppose I have this compound, and obviously this first one I got in there is going to be in a ketone functional group. And when I go ahead and count the number of carbons and oxygens and hydrogen, it comes out to be C6H12O. Obviously, I know I have two non-bonding electron pairs on this oxygen atom, and when I lose an electron after running it through into the mass spec, and typically the way we lose an electron, we kind of bombard this molecule with an electron, and as a result it loses one of the electrons. So it loses one of these non-bonding electrons in that case, and what I'm going to get at the end of the day is, okay, I'm going to go ahead and remove this electron, one of them, and so that kind of creates a radical, and also it kind of gets in a positive charge there. So this makes, and then obviously you're going to have one electron that kind of gone away. So this is your radical cation that you would make in this particular case. And you would see this in the mass spec because you got a positive charge on this. And the M over Z ratio on this one is going to be whatever the mass whatever the molar mass going to be for this compound, because losing an electron doesn't really change the molar mass a lot. So C6H12O, and when you do the math, it's going to come out to be 100 if I just focus on the whole number. And you do see a peak at about 100. So you do see a peak right there. That's at 100. So this is your molecular ion peak. Or I can also say M plus peak. And I can possibly, I would also say this is going to be your parent peak. So you got a couple of names that you want to make sure you're aware of it. Now, the other thing I got to worry about, like what other peaks I'm really seeing in this spectrum here, and I need to figure out what those fragmentations going to look like. So let's talk about the alpha cleavage first. So the way the alpha cleavage work, obviously, when you make this radical cation, this can undergo a further break fragmentation. And one of the fragmentations I could possibly see here would be if I go ahead and break this structure right here. So when I'm breaking it right there, I'm going to end up getting a psyllium ion that's going to be something like this. I don't want to draw an angle here, but I'll just draw in a slight angle here just to kind of so that you can see it here. So that's going to be in an O within a positive charge. So this is your psyllium ion, and that would be having a resonance, and the resonance structure on that obviously looks like this, where the carbon can get a positive charge. But typically we draw this one a lot because this is going to be the more stable resonance structure, because it's got all the octets completed for this particular case. And the radical that you're going to create along with that would be in a 4 carbon. So that's going to look like this right there. So it's not that I cannot do the other way around. Like I can also create another possibility here would have been, what if I actually create a radical and the carbocation opposite? So if I created a carbocation here, that would be positive. And then if I create, I'm not going to draw both of those resonance, but let me just draw one of them here. What if I create this as my other radical here? Okay, and obviously it's going to have one electron there. So the problem with this part here is you're not going to have this carbocation that you just created is not going to be stable compared to the carbocation that you have created up there. So this is going to be more stable carbocation. So as a result, you would more likely to see that in the spectrum. So what I'm really losing here, if I want to kind of look at here, the molar mass of this radical cation was 100, and I lose this 1, 2, 3, 4. So 4 C4 H9 here, radical, so that's going to be 57. So that's going to be 57. So that means I should have this as 43 as beryllium ion. And when you go back here, you do see that this beryllium ion here, or this signal that's going to be having an intensity of 100%, that would make this as in a base peak that would be at 43, and that would be this particular psyllium ion there. So that's how you want to figure that out. Now, do I see 57 in there? That's the question. Like, what if I actually make this carbocation here, even though we said this is not going to be stable, so you should not be looking at it in here. But let's just see to double check. If I go ahead and make this, then I should be at a 57, because remember, the radical doesn't really show up in the mass spec. It's only going to be the carbocations that shows up, or the radical cation that shows up in the mass spec. So this at 57, let's see if we have it. So we got 55 here, and 56, 57. So you do have this signal right there that's going to be at 57. So it's not that you don't see it at all, but you see a little bit. And the reason why you see it a little bit, because this is not very stable. So the primarily base peak that you're going to be coming here is going to be coming from this psyllium ion. So that's really what we got going on here. So then what else can we see? What if you actually break the psyllium ion from the other side? Is that a possibility? What do you mean that when we say other side? Well, instead of breaking it from the right side, what if you actually break it from the left side? So when you break it from the left side, I can still make an psyllium ion and then a radical. So the radical I'm going to create here would be the CH3 radical. That's from the left methyl group. And then what's left behind as an psyllium ion here would be, I'm just going to go ahead and draw the carbon here with technically a triple bond. So that's going to be 1, 2, 3, 4, 5 carbons basically. So 1, 2, 3, 4, and 5 carbons there. And then obviously you would have a positive charge. So that's an psyllium ion here. So you lose on the radical, you lose 15. The CH3 is going to be 15 here. So that means I should have this psyllium ion showing up in the mass spec at 100 minus 15. So that should be around 85. So let's go back and see if we see anything at 85, and you do have a signal that's right there that's going to be at an 85. So that's how you really check what you're really seeing and whatnot in terms of the fragmentation. Now, what if you do the McLafferty rearrangement? So the way the McLafferty rearrangements are usually done, if you actually have a beta and a gamma carbon. So let me just go and copy this down here, and I want to go ahead, call this alpha, beta, gamma, and you can call this delta, the last one, but we don't really worry about it. So then the fragmentation or the McLafferty rearrangement typically takes place between the alpha and the beta. So you have to have that alpha and beta, and for this to actually take place, you have to have a gamma as well. If you don't have a gamma, then it would not technically take place, because it's really the gamma that makes the interactions with this oxygen right there. But what's going to happen then, I'm going to actually go ahead and break it up right there. And when you break it up right there, it doesn't really create a radical, it creates an alkene. So what it's going to create is, from the right side, I'm going to get a propene, because I got 3 carbons on the right side. And I can number those as, let's say, 1, 2, 3 for my own convenience. So 1, 2, 3. Not numbering those according to the IPAC rule, just for my own convenience to keep track of carbons. And then that makes a full molecule, and that leaves you with basically a radical cation again. So the radical cation that's going to be left behind here is more or less going to look like this. So that's what we really got in there. So basically what happens is you break this bond right there, And when you break this bond, one of the electrons goes on here to make the pi bond, and the second electron it gets to make the pi bond is going to be from this pi bond right there, and then one of these electrons right there is going to be gone on to the hydrogen of the gamma. So I'm not really showing the mechanism, but just kind of see where the fragmentation really going to take place. I'll have it in a separate video where I'll talk about the mechanism, but for this to happen, you have to have it in a gamma at least. You can have further down, but you have to have it in a gamma carbon for the McLafferty to take place. If you don't have it in a gamma carbon, then the McLafferty is not going to take place at all. So what I lose here is C3, and how many hydrogens? So I got 2, 3, and 6. C3H6, so that's going to be 36 plus 6 is 42. So that's a loss of 42. So that means this cation that I'm going to be seeing here should be at 100 minus 42. So I should be seeing somewhere around 58, and that is going to be my McLafferty fragmentation there. So let's see if we have anything at 58. So I do see a signal that's at 58, and that is going to be your McLafferty there. So that's how you really figure that out. Now let's do the aldehyde as well, and aldehyde is going to be very similar to what you see in case of an ketone. You're going to be seeing it in an alpha cleavage, and you're going to be seeing it in a McLafferty rearrangement. So let's say I got this compound here. I'm just going to make this a little bit smaller. And again, this is in a pentanol. We got 5 carbons, 10 hydrogens, and oxygen. So if I do the math here, so 5 times 12, that's 60 plus 10, that's 70 plus 16, that's going to be 86. So I should have the M over Z to be 86 for this compound. So let me just go ahead and make the radical cation here. So when I go ahead and make the radical cation, I lose one of the electrons from the non-bonding oxygen non-bonding pair. So that's how you make the radical cation. I got the lost electron there, and the M over Z for this radical cation should be 86. Now let's see if we have anything. So we do see a signal that's going to be at 86. So that would be your parent peak. You can call that. You can also call that molecular ion peak. Now, one of the things that you see typically if you have an aldehyde, that this is right here is going to be your M plus peak. You should see a peak that's going to be 1 below that. So you do see a peak at 85, that is going to be M minus 1 cation peak there. And why do we seeing that? Well, that's really in an alpha cleavage on this molecule. So if I want to go ahead and break this apart, I know there's a hydrogen here. So when I go ahead, I'm just going to actually use the radical cation here. So when I run the fragmentation, one fragmentation at the alpha cleavage would be if I do it right here. So if I go ahead and get rid of this hydrogen, I'm going to end up making an acylium ion. So I'm just going to go ahead and copy this down here. And that acylium ion would now have a triple bond. That's how you make the acylium ion. So you would have a triple bond here with oxygen with a positive charge, and obviously you can draw a resonance on that, and you have a hydrogen radical. So I lose 1 here, so that means the molar mass of this acylium ion here would be 86 minus 1, and that would be 85. So that's how you know that you actually have an aldehyde versus a ketone present. But then at the same time, you can also run this the other way around, and let's see if that actually works out in this particular case. Now, sometimes you may not see that particular fragmentation, and sometimes you also see some other fragmentations in there that is not commonly explained by the alpha cleavage and just the McLafferty. But I'm here only talking about the most common ones that you're going to be seeing for these functional groups. So if I go ahead and do the fragmentation right here, so then I'm going to be 1, 2, 3, 4. So the radical I'm going to make would be this one right there. And obviously, remember, I can also make a carbocation out of this, but that is not going to be very stable carbocation. And then I'm going to be making an acylium ion here. That would be just a hydrogen, carbon with a triple bond, and an oxygen there with a lone pair. So then this is C4H9. So that would be 57. So that's a loss of 57. So that means this guy right here is going to be 86 minus 57. So you can do the math, or you can also be like, okay, well, this is going to be 12. That's 13. And then oxygen is going to be 16. So that's going to be 29. And also 86 minus 57 is going to be 29. So I should be seeing another signal at 29. Let's see if we see that. And yes, we do have it right there. So see that cesium ion at 29? That is going to be because of the alpha cleavage as well. All right. And then if you want to argue that, do I make any sort of carbocation out of this C4H9, maybe even a little bit? The answer would be yes. And if you are making just even a little bit of a carbocation out of this C4H9, like we did in a previous example, then that 57 peak should show up on mass spec, even if it's in a little bit. And let's see if we have anything at 57. And it seems like, yes, we do have at 57 right there. So that is because of the C4H9 carbocation that you're going to be making a little bit that is showing up there. Well, none of those are actually the base peaks. The base peak that you have here is going to be this guy that has the 100% intensity, and the base peak is at 44. All right, so when I do the math here, I'm losing 86 minus 44. That would be 42. So I'm losing 42. I need to figure out where that 42 is coming from. And that's another thing. Typically, when you lose water and when you're doing the McLafferty rearrangements, you lose an even number of molar mass. And a lot of other times when you're using losing methyl, or you're losing ethyl and propylene, stuff like those, you lose an odd number of molar mass. Like for example, when we lost the hydrogen, we lost an odd number molar mass here. When we lost this propyl group right there in this example, we lost um, right there, sorry, rather. When we lost propyl group right there, we lost 57. That's an odd number. When we lost methyl, we lost 15. That's an odd number. So that's another thing that you can kind of keep in mind. So where this is coming from, it's losing in an even number, even molar mass. This is very likely coming from the McLafferty rearrangement. So let's talk about that. So I'm going to have this guy right here, and I can kind of show you the mechanism a little bit here. So I'm going to draw this in an acyclic form actually. So this is alpha, that's beta, and that's gamma. So what happens is the hydrogen that you have here and the oxygen here at the gamma position, when you count it out, it's going to be 1, 2, 3, 4, 5, and 6. So it makes a 6-member ring. So this hydrogen that's going to be at the gamma carbon is going to be closest to this oxygen right there. So that's why I was telling you earlier that you have to have it in a gamma carbon for the McLafferty to take place. If you don't have it in a gamma carbon, then it's not going to take place. So how does this really kind of work out? It's at this point we start seeing some of these arrows that's kind of flying around. I can have this kind of going in there to make a double bond. So we're kind of doing a homolytic cleavage here. And then this bond breaks, doing a homolytic cleavage right there. This bond breaks, doing a homolytic cleavage. And then this bond between the carbon and hydrogen is doing the homolytic cleavage as well. And then I'm going to be using one of these electron here from that bond and one of the electrons from the hydrogen right there to make the bond with the oxygen there. So the cleaving that you see is going to be right here between the, let me see, between the alpha and the beta carbon. So when you see the cleaving here, I'm going to go ahead and draw. So remember, this was the beta carbon as the designation that we have given it earlier, and this was the gamma. So we created a double bond here between the beta and gamma, and that leaves the other carbons that were attached to the gamma as it is. So you have to have at least one hydrogen for this to take place at the gamma position. So this is going to be one of the products, and your second product that you're going to be seeing in here would be looking something like this. So you don't really create a carbocation here, you still create a radical carbocation here. So you're still going to have the hydrogen now that's connected with that oxygen. You still have one full lone pair and one radical in there that makes it a positive formal charge on that oxygen. Okay, so then this will not show up in the mass spec, so that's going to be C3H6. That's going to have a molar mass of 42. This will show up. That would be your McLafferty rearrangement there. And I can do the math here, or I can even count the number of carbons and everything. So that would be C, 1, 2, 4, oh. So that would be your 2 carbons is 24 plus 4, that's 28 plus another oxygen, that's 16, so that's going to be about 44. So you should see at 44. And then you can also do the math here, where if I do subtract 86 minus 42, that will give you 44 as your molar mass. And let's go back here, and we do see the signal here that's at 44, and that was actually your base peak that has a 100% intensity. So this was actually coming from the McLafferty rearrangement. All right, so that's how you do the alpha cleavage and the McLafferty rearrangement for this one.